Right. Good morning, everyone. We're just waiting for additional participants to come in, but we will get started just in one moment. Okay. Welcome to this webinar. This webinar is on two projects, Phoebe and Julia. And the topic of the webinar we'll be discussing today is safe streets, safe lives, road safety models for vulnerable road users. So my name is Monica Olislagas. I'm the Global Innovation Manager at the International Road Assessment Program. We are the technical lead for the Phoebe project. And so what I will be doing today is running through that project and introducing you to that. So I will start with the Phoebe project and run through the models that we are using in that project and also the tools, mainly the traffic simulation and visualization solutions. Then we'll have an introduction to the Julia project by Factual and the application of satellite technology. And then Factual and Key to Mobility will end with a presentation of the CycleRAP model and lane patrol tools and look at the two different use cases in Spain that each of the projects have. Just a note that we are recording live and you are welcome to ask questions. So we will run through each of the presentations and then at the end have some time for questions. So this webinar, as I said, is focused on two projects. Phoebe stands for the Predictive Approaches for Safer Urban Environments. The Julia project is the joint developments for urban resilience, connecting users to public transport through space technology. So both projects are very innovative in terms of how they are using data in order to improve road safety. For Phoebe, there was a specific need when we started with this project and responded to the call. The need that was set out was very much around how do we manage the future of urban traffic systems in all their complexity. Urban traffic systems are changing regularly. Our cities are having to deal with all sorts of challenges that they haven't necessarily had to deal with before. And the rate of these changes are happening very, very fast. So the call topic was really focused on the development of tools that assist those that are managing road networks and transport networks to better anticipate the impacts of changes. And some of this was around both intended changes, so planned things, as well as those unintended changes that happen. I mean, we all know during the pandemic, for instance, that there were a lot of changes that happened really quite quickly to the road network in the way that people were traveling, but also the types of vehicles that people were using as well. There is a disconnect currently between what sort of tools that are at the disposal of road managers and the reality on the ground, and really a stark difference is in how the active modes such as walking and cycling can be represented in simulation models. And so if you're managing a road network and really trying to be able to incorporate these modes in a more meaningful way and use simulation models to understand their impacts, it's really important that these models are now updated to enable that. So the Phoebe project is essentially a framework. It's a methodological approach to help cities better understand the future safety implications of changes. And so that's where, for the Phoebe project, it is very safety focused. So we're looking at all sorts of possible changes. It's not just how we redesign a road or whether there's different types of vehicles, but it also includes things like changes in road user behaviors and travel patterns, and can be a regulatory change as well. So essentially what we're hoping to get to by the end of the project is a clear blueprint for how cities can establish and apply a predictive safety assessment framework efficiently and cost effectively. And this issue of a predictive framework is really important. And it's important because the way that if you are waiting for crashes to happen and people to get injured before you can address the safety issues, that's what we call a reactive approach. And it's one that has a big cost. It requires people to get killed or injured before something is done about it and before the issue is identified. The International Road Assessment Program, the organization I work for, we have models and have had for about 20 years that are evidence-based and help cities and others identify issues, safety issues on their networks because associated with the design features of the roads. And so that's where it's important that we can incorporate these tools that already exist into traffic simulation tools and similar in order to be able to marry those two things up and have a far more effective way of identifying and treating risks and waiting for crashes to actually happen. You can see there we've got a good spread of partners. There's 11 partners in the PHOEBE project, and we are well distributed across Europe. We've got several different pilots across Europe as well, in the UK, Athens, and Valencia in Spain. So we're about halfway through the project currently. We are at the point where we are testing the framework in its individual components, and you can see some of these here. So we have the risk assessment preliminary results. We've been working on behavioral probabilities in order to better inform the simulation models on pedestrian and cyclist behavior. We've also got the mode shift and induced demand models that are going on in order to predict mode shift and preference, and also the simulation enhancements. In terms of what we hope to achieve once the PHOEBE project is completed, is really about being able to have a set of new and enhanced tools where cities and road managers can visualize what the outcome, the safety impacts of different outcomes. To do that, we really need a good harmonization of road safety indicators and measures that we can benchmark on, and also be able to report and track safety issues and compare it to alternatives. We also want to achieve a detailed socioeconomic impact of safety measures. So to some extent, the iRAP models already enable this, but this can be really enhanced in the way that the PHOEBE project and the sort of tools the PHOEBE project is pulling together into this framework. So in essence, we're looking for better design principles of future road and transport systems. That's a really important one. The name PHOEBE, actually, my daughter is also called PHOEBE. She's 12 years old. And sometimes it gets very confusing with email subject lines when I'm reading the word PHOEBE and not understanding which one it's talking about. But in terms of thinking about this project, when we are designing roads and we're making decisions about that, we're really making decisions for the next generation. I grew up in Australia, where the road environment or the transport environment in our cities is very, very car oriented. And those decisions were made back in the 1950s with the road plans that were created back then. And essentially what I grew up with was a product of decisions that had predated me. And so this is something that really brings it to the forefront of my mind, that the decisions that we make about how we manage our road system and how we develop that road system now really is for the next generation. We also want to improve reliability and performance of systems. So we can no longer afford to have duplication of effort and different departments in the same road authority working on completely different things and purchasing data separately, and a disconnect between safety. Safety really has to be at the very center of these decisions. And of course, the last element in all of this is that we need to achieve some pretty big targets in terms of road safety. So the European target, as well as at the UN level, is to reduce serious injuries and fatality crashes by 50% by 2030. And the European target is to eliminate fatal and serious crashes by 2050. So in terms of what we're looking for and how we connect the PHOEBE project through to this, we're looking for really tailoring those risk factors to urban areas, making sure the behavior models are well integrated into risk assessment and the traffic simulation. Being able to allow cities to see the safety impacts of prospective changes and really understanding the before and after effects of changes in the network. So as I said, we've got 3 use cases: Athens, Valencia, and the West Midlands region in the UK. Today we'll be drilling down a little bit more into the Valencia use case than the others, because if the application of the CycleRAP model, which Factual and Keita will touch on later in the webinar. But just to give you a little bit of background on the Valencia use case. So Valencia is a city of 800,000 people and a really important tourist destination. It is by the sea and is a pedestrian and bike-friendly city. So active mobility accounts for more than 50% of the trips. There's 8.3 urban road fatalities per 1 million inhabitants in Spain, and this is something that really needs to be addressed. So in terms of what the PHOEBE project is doing in this pilot study, we're looking at the scenario test for initiative of bicycle infrastructure investments. So Valencia has heavily invested in bicycle infrastructure in recent years. So as part of that, we'll be looking at 10 intersections and the bicycle and vehicle interactions in those, and also an assessment of road user behavior, and specifically focused around the use of micromobility. So that's a very brief snapshot. As I said, please, if you have questions, save them and we will answer them toward the end. Please engage with us. We've got another webinar coming up on the 25th of February as part of the cluster joint webinar, and it's focused on introducing innovations for road safety in complex urban environments. So the QR code there in the top right corner, you can scan that and sign up. Otherwise, you can go to the PHOEBE-project.eu website and you'll see a link there as well. Otherwise, follow us on social media as well. So we are at Project PHOEBE, and our LinkedIn address is there as well, and all the QR codes are at the bottom. Okay, so now I'm going to hand over to Factual to introduce us to the Julia project and the application of satellite technology. Over to you.
Thank you very much, Monica. Just going to share my screen. Okay. So my name is Manuel Filgueiras. I'm a mobility consultant at Factual Consulting. We are a consultancy company focused on mobility innovation, and today I'll be presenting Julia to you. So just an overview of my presentation. I'll start by explaining what is Galileo and Copernicus, then some facts about Julia project, the overview objectives, some applications that will be developed within this project, and finally the pilots, where we'll test them. So just to give you a brief introduction, what is Galileo? Galileo is Europe's global navigation satellite system. This is similar to GPS, only that GPS is the US system. So this provides positioning, navigation, and timing service worldwide. And what differentiates Galileo from other systems, such as GPS, are these differentiators that, for example, high accuracy service is a differentiator that provides improved position accuracy down to 20 centimeters level, compared to other systems that usually provide meter level accuracy. So sometimes when you're in an app, Google Maps, for example, your position sometimes is not precise. It's like 5-10 meters away from where you are. And this is where Galileo takes his role with this differentiator. Another one, for instance, is the open service navigation message authentication. This is a security feature that protects against spoofing attacks. These are fake GPS signals. So Galileo verifies if the satellite signals are authentic. And this is crucial for applications like aviation and emergency responses. So essentially, Galileo will stand out, and already stand out because it offers high accuracy, it's more reliable, and provides better security while being a free system, okay? Free of charge. On the other hand, Copernicus is the Earth observation program of the European Union. This is a system that helps monitoring the Earth from space. Unlike Galileo, which is for navigation, positioning. Copernicus is all about collecting environmental and climate data to help scientists, governments, developers, and business to make more informed decisions about environmental data. And it measures a lot of things. For instance, on the land side, it can measure deforestation, agriculture, and urban expansion. On an atmosphere side, it can measure air pollution, greenhouse gases, but also to extreme events such as natural disasters and extreme weather. So, all in all, how Copernicus satellites differ from Galileo? Well, the purpose, Galileo is for position navigation, and Copernicus helps with environmental monitoring. Also, the end users, it will be different. So for Galileo, you can think of an end user that will use their smartphones in their cars, their aviation for location tracking, while Copernicus will be mostly used by scientists, governments, application developers, and business for monitoring climate and provides other insights that can also be applied to urban mobility as well. So the Julia project, just to give you some figures, it's a project funded by the European Union Agency for the Space Program, EUSPA. This is a 30-month project that has started January last year and counts on over 14 partners. The objectives are really to demonstrate this role of Galileo differentiators to the upstream of public transport market. Okay, and how we are going to do this? We are developing currently 8 applications that will be piloted in different European cities, leveraging these differentiators of Galileo, aiming to have at the end of the project market-ready applications in some cases. The second objective is also to leverage the Copernicus data to provide valuable data for mobility planning and climate action. And in the end, finally, we want to uptake the market for public transport operators to scale these applications that use data from satellites such as Galileo and Copernicus. Then we'll also provide and create a global observatory. That's an ongoing effort where we'll quantify the reach of Galileo and Copernicus in public transport sector. Let me just say that here, public transport sector, I said in a broad sense. It also will include applications for cycling, as Jose will explain later on. So it is also available in very different applications. These are the partners of the project. We count with 12 partners from public transport operators to technological partners that are experts in Galileo and Copernicus. Just to provide you with an idea of the applications that we are going to use, the first one, seamless public transport trip validation Galileo. Here, users with mobile devices can automatically validate tickets for the trip when it computes positioning data when users are in the bus, tram, or train. And this will already use one of these modules that I referred to, which is the Open Service Navigation Message Authentication, OSNMA. And this will be very useful for being able to charge users of public transport in accordance to the distance traveled. So if you're entering one stop and you're leaving on the next one, it will compute the fare charge compared to the distance that you travel. And this will be authenticated and confirmed by this differentiator. Second application, AI techniques. Here we'll feed big databases of origin destination data that is provided by Galileo-enabled devices. And this will be exploited to support mobility planning, select the most appropriate route offers for transport planners, and provide more accurate real-time pickup and arrival information. Then a third application, which is AI algorithms for better GNS map matching. So here, AI will be used to improve the map matching process. This is to reduce the geotagging errors. You can think of applications that include precise location, for example, for a bus stop, that so far are generated by relative position of vehicle that can be precisely calculated. Moving on, the fourth application is quite self-explanatory. It's accurate vehicle tracking with Galileo. So with using Galileo, PTOs, public transport operators, can provide and transmit their position near real time. And applications here can be used to display live geographical position through user apps and provide a better estimated travel time of arrival. Can also help fleet operators detect incidents such as important delays, breakdowns, as soon as they happen and inform users. Then the fifth application, effective DRT pickup. So sometimes when you order an Uber or demand responsive transit, the stops are usually virtual stops that are predefined or depend on your location. Obviously, if we have a more accurate and reliable GNSS position, this process will be enhanced and easier to deal with. Then our sixth application, it's to validate, and we will test by deploying an autonomous shuttle in Slovenia, and we'll use Galileo to validate the positioning of this shuttle. And the goal here is to identify errors and improve the stop accuracy for better rule alignment with the theoretical route and the expected stop location. Then probably the most important application within this project of Phoebe and Julia combined is the AI and computer vision enhanced cycle lane assessment for safety. Leveraging on the CycleRAP methodology explained before, this methodology requires taking images of the assessed cycle lane every 10 meters. So it's really in critical importance to know where exactly these photos were taken. So if the geolocation is not good, then these 10 meters can deviate and give a wrong assessment of the cycle lanes. Additionally, labor costs for coding these images is high and prone to errors, and we wish to automate this coding process through AI and computer vision to advance this tool that is Lane Patrol, aiming at making it more attractive in the end and providing a safer cycling infrastructures by providing an accurate assessment. Then the last application using Galileo is the accurate vehicle tracking to improve safety of pedestrians. So as you know, cities nowadays are populated with micromobility options such as e-scooters and bicycles. Sometimes this can be dangerous for pedestrians if users don't respect the limits and ride on the sidewalks. So usually what happens is that there are dedicated regulations that are applied for the platforms that rent these systems, defining when, where, and how this can be used and park these vehicles. And these platforms obviously rely on the location of the mobility asset and use polygons that create the rules to be applied. For instance, a polygon where you can park an e-scooter or a polygon where you cannot ride the scooter. However, if we don't have a good accuracy of the location of these devices, we cannot allow the use of smaller polygons. For instance, small polygons here could be covering a bike lane or a sidewalk. So if we have a good accuracy, we can know where are the bike lanes, where are the sidewalks, where are the restricted areas, and enforce the laws and the rules for these systems. Additionally, the cities can collect infraction data and be able to improve the safety of this system. Then we have two more applications using Copernicus. The first application basically is a air quality based model decisions in public transport. And this will integrate the location information of Copernicus with air pollution sensors were available to provide real-time and predictive information to travelers, such as through transportation apps or of suggestions of which routes to take, for example, green routes, routes with less pollution, and this can also be helpful for cycling. The last application, climate change and monitoring urban areas. This application will use AI-powered models based on Copernicus data to monitor the evolution of environmental quality of cities, visualize trends, and benchmark between different cities. So it's more like more at planning level. Then I just wanted to show you the observatory I was talking before. So within this project, we are creating a database that will quantify and monitor and track the progress of the Galileo adoption in public transport worldwide through reliable and quantifiable indicators. It's also the first of its kind, and the final end is to support and provide public transport operators with ideas and market uptake of these technologies and how they can benefit the public transport sector. Also gather data from multiple sources, creating one stop for platform for this Galileo and Copernicus uptake information, and also provide air quality indicators based on Copernicus data in at least 13 European cities. Then we'd also like to engage and maximize dissemination of Galileo uptake in public transport systems and promote international best practices. Then just to show you the pilot cities that we have, we defined 3 levels of pilot cities. The first pilot cities where we'll test the first 8 applications, Galileo, are in 3 distinct geographical regions, the Catalonia urban and peri-urban areas, the Greek main metropolitan areas, and in Slovenia, urban and peri-urban areas. Then the second level 2 pilot locations will focus on developing Copernicus-enabled air quality index for cities, and this is to enhance the climate monitoring in 10 European cities that are from the 100 climate neutral and smart cities by 2030 list, helping them to monitor air quality factors. Then, on pilot level 3 locations, we'll include other cities, metropolitan areas, or regions across the EU that Julia will reach out for an open call for small-scale pilots, which will benefit from the experience of the other 2-level pilots. So, in a nutshell, this is the Julia project. And now my colleague, Jose, will continue explain a bit more one of the use cases within the Julia project and how the cycle lane will help. Are you ready, sharing? Thank you very much.
Thank you, Manuel. Then yeah, I'm ready, and I think I'm. Can you see my screen? I think I'm sharing it already.
Yes, yes.
Yeah, great. Thanks a lot. Okay. So what I'm going to be talking about is Lane Patrol is one of the tools that has been used in both of the projects. So in a way, what I want to talk about is why we're doing Lane Patrol, our tool, our product, why it is relevant to be part of these European funded projects. And actually it is a way to show that companies and products can find a way to create or innovate thanks to these projects. And then I'm gonna end by mentioning what we're doing now. Where are we now with Lane Patrol? So a bit of context of Lane Patrol. You've seen, and we've seen, hopefully, that cycling is becoming, I would say, a trend. It is part of the political agenda nowadays. Of course, there's a lot more to be done. But we see that the European Parliament wants to double cycling by 2030 compared to a couple of years ago. And also last year, the European Commission published the European Declaration on Cycling. There are many points in this declaration, but in general, we see that cycling is becoming part of the agenda. So we have the mayors or people in the government saying, oh, we want to build a cycling city. And when they want to start, they realize, okay, there's a lot of comments. There's one mom saying, oh, it's not safe to cycle to school with my kids on that area. There's another person in the community saying that in that specific avenue or intersection, there's a lot of traffic accidents. And then there's a guy saying, I'm cycling to work, but it's, I'm on the cycle lane, but then suddenly it's not connected in that part of the city. So where do we start, they say? And that's where we come with Lane Patrol. What we do with Lane Patrol is we do smart assessments and improvement plans for cycling infrastructure, basically using data to understand where are problems with the cycling infrastructure safety and attractiveness. How do we do it? There are three parts, main parts. So we collect data, different types of data, from getting data from external sources, but also collecting images that we then can use for the assessment. Once we collect the data, we map it, we characterize it, and then we evaluate it. With this data, we already have the data, we need to organize it and get the insights. So we do risk analysis, and then we also prepare improvement scenarios. So forecasting what will happen if we do some specific work on specific areas. In our tool, in order to do these 3 stages, we have 5 steps. We design, basically we say where we're going to analyze, which routes, the whole network or just specific cycling routes. We go and collect the data. We do the coding. What we call the coding, it's defining attributes or characterization of the cycling infrastructure. Then we go to a quality assurance process, the review process, to then actually finish with analyzing the data. So we start saying, okay, this is just one example. We can select one specific route. We design what we're gonna analyze. Once we design it, we go and collect the data. We have developed, among other things, a mobile app to collect geo-referenced images. I will explain a little bit better. After that, after we collect the data, we do this coding. But I said that, okay, there are different attributes, and then we do it every 10 meters. So these 40 attributes, what are they? And this is what Monica was mentioning at the beginning. We are following the CycleRAP methodology, the model, their standard. What is the CycleRAP model? It's a way to analyze the cycling infrastructure based on over 40 attributes, divided into different categories, including speeds and volumes. That means how many cars are passing by, if there are cars passing by right next to the cycling infrastructure. Also, other pedestrians, how many bicycles are passing by. Then we have facility context. This is what do we have around the cycling infrastructure? Are there sidewalks, parking places, the road that I mentioned earlier? Then we follow with the intersection attributes. So we see there's a traffic light, there's pedestrian crossing, and everything that is just you're on a cycle route, and then there's something crossing there. And then the last bit is the facility feature attribute, which is basically saying how's the surface, if there's an object blocking the cycle lane, if we have some painting on the surface, if there's some barriers or some sort of segregation for the cycling infrastructure. All these elements, all these characteristics or attributes are coming from the CycleRAP methodology. And Lane Patrol and we, with our tool, we are trusted suppliers by iRAP. iRAP is what Monica is representing. Monica is part of the International Road Assessment Program. And basically, in general terms, CycleRAP, it's a decently new methodology. It's been already for a few years in the market, let's say. But iRAP has been working with different methodologies. Their methodologies have been used in over 100 countries. There are other methodologies, such as the star rating, to analyze the safety of highways or roads. It's been implemented in over 1 million kilometers of roads. So there's already knowledge on analyzing the safety of the built environment. So together with iRAP, led by iRAP and with the board of people supporting CycleRAP, this methodology, CycleRAP, was created with all the knowledge that was previously understood or learned with the iRAP models and methodologies. So we brought the evaluation of roads was brought into cycling infrastructure. So analyzing the safety of cyclists and light mobility users from all the learnings from previous methodologies, and always from the point of view of these users, cyclists, and anyone in an e-scooter, for example. So the idea of CycleRAP is to make something easy, affordable, and fast to analyze the cycling infrastructure safety. Who will be using this? So it is intended for urban planners, policymakers. That will be like the direct answer. But there are also many other stakeholders that can benefit from this. Sharing schemes of bicycles or e-scooters, insurance companies, delivery companies telling their users, you know, yeah, I know there's a cycle lane over there, but you know what? If you do a 30-second detour, it might be way safer. That's just examples. So as I was saying, we code these attributes that are part of the CycleRAP methodology, and then we do review of the coding. So this is quality assurance. This is just part of the process that we do. To finalize with the most important part, which is getting the safety performance indicator. So analyzing actually our infrastructure. And also following with the CycleRAP methodology, we get an overall score that gives us the score of these 10-meter sections of the infrastructure. And then obviously we can have an overview of the whole network. But we not only have the overview of the risk, we also have 4 different elements that are analyzed for the same 10-meter sections, which is, you can see a little bit on the right. We analyze the conflicts of bicycles with vehicles, with other bicycles, with pedestrians, and with others. So basically objects or a wall, for example, or a tree. And this is how we do the process. Once we have this analysis, so we have these 10-meter sections, and then we tell them, okay, we can go to the detail, saying like all the information, all the risk, all the safety performance indicators. We also, directly with the data that we have, we suggest improvements. Based on the data, based on the characteristics of the topology of the infrastructure, we tell them, you know what, if you just widen a little bit the cycling infrastructure, or you make it one way instead of two way, because you can probably crash to another bicyclist, you can just make it one way, and that would be a little bit safer. And we give the expected or the forecasted score. And also at the bottom, we say, okay, if you don't want to implement that already, or you don't want to do this scenario, what we can tell with the data is saying, from the 40 attributes, over 40 attributes, we know that 50% of your risk comes from having cars right next to you running at 50 kilometers per hour in average as an operational speed, and there are like 10,000 of them. So just with that, if you can reduce that, those are already half of the risk is coming from those, based on the CycleRAP model. So this is also information that we're giving. And a little bit of an asterisk. The CycleRAP methodology in urban areas, let's say that it's a little bit strict with the 10-meter section, because in urban areas, there's a lot going on. So you can find things like a post, like a crossing, like a bus stop, or many other situations. And then there's a difference. Every 10 meters, you can find differences. But if you go to more rural areas, to a park, these 10 meters can be extended to 2,000 meters per section to be analyzed, according to the model. PHOEBE. So as I was saying, we can do this analysis at a section level, but we also do plans at a network level. So you can analyze either just one block, 100 meters. You can analyze a whole route, 1-2 kilometers, or you can analyze the 300 kilometers of cycling infrastructure that you have in your city. And we can give data for this, aggregated data, some insights for this. Now moving forward to, okay, how was lane patrol used in the PHOEBE project? Basically, we started with analyzing different typologies of routes that were connecting routes, as cycling routes, connecting to the Polytechnic University of Valencia, UPV. So a bit of context. Monica already shared that Valencia has 800,000 inhabitants, but actually the metropolitan area, it's 3 times bigger than that. Something that very interesting is truly like a city with at least 50% of the trips done in active mobility. It's something amazing. It's not only bicycles, but also pedestrians. So it's a very walkable city as well, but also quite cycling friendly. Something interesting is that there are 100,000 university students. So this is a big chunk of the population. And UPV only has 48,000 students. So that's where the university is. We see that we analyze these 4 different routes. There's there are different colors there. We can see the route. There's the red route, the yellow one, the blue one, and the green one at the bottom. It's not super clear, probably in this small image. But we see that, okay, that's a university, but also we see the beach to the right side. So it's actually There are some tourist hotspots not too far from the university. There's a tram crossing near the beach, and then we see a high flow of pedestrians, obviously from the tourists, but mainly near the university. We can think of many students passing and getting to the university. So we did the whole process that I mentioned earlier. We did the whole process for the 4 routes, and then we get this data. We get this overview of the data. We can see where we have mainly the highest risk scores, which are the routes that probably need more attention, which are the routes that are a little bit better. And what I want to do is to show you some examples. So then we have this example here. It's this one here. We see that it's actually quite a decent cycle route, but still vehicles are passing by quite adjacently at a high speed. We see that there's 2 road lanes on each side of this big avenue. So that's probably one of the big problems with this. In this one, we see that there's no conflict. If you see in the lower corner, lower left corner, the green part, the upper text says conflict with vehicles, none. So this is something interesting. We don't have conflict with vehicles. That is amazing. However, in this specific spot, there's a tree that might be problematic. That's why we have here in the bottom, we have that it's red at the bottom, crashes which do not involve others. So we can see the tree here. That's where we are. This is quite a new cycle lane. It's completely segregated from the cars, like a very good barrier to protect from the cars. And it's a 2-way cycle lane. Could be improved for 1 way, but still is quite wide. It's over, I believe it's 1.5 meters per direction in this one. So it is quite a decent cycling infrastructure. Then we have another one here. We see that there's it is quite well painted on the surface. However, the conflict with pedestrians is marked as yellow or medium risk, because obviously if you're gonna go get your car because it's just parked there, even though there's a painting, there could be a crossing and there could be a problem between pedestrians and bicycles. Okay, this is where we are. Okay, one more thing that we did with this analysis, we have with our data this over 20 suggested treatments coming from the data. This is something also from CycleRAP. There's a model created by CycleRAP saying, okay, depending on the data, we can already suggest what you can do. So in this example, we found that upgrading existing facility to an on-road bicycle lane with safety barrier would be the one that is mostly affecting positively the sections in the infrastructure. We see on the top, we have over 400 sections where no treatment was suggested, but this one has 276. So the one I mentioned is the top treatment. And it's basically what we say is that for each section, we check what treatment will be the most effective. So here we see that this one is the one helping the most. And then what we do is that we create this scenario. We build it. It says, what would happen if we will implement this treatment in those sections where it was suggested based on the data? Okay, and then we can see. So before you actually do any work on the road, we can already plan it and see what would happen. So this is something that we were using as part of the PHOEBE project. I know that this data was also used to build a model with Amazon. So that I was not too much involved into that, but also the data that was obtained from this analysis was used for more wider, more comprehensive simulation. Okay, now we move forward to lane patrol in the Julia project. We did 2 things, basically. We are doing, because we're still on this project. It's an ongoing project. So we wanted to check, we wanted to make sure of the improved geolocation of the georeference images that we were using. And also we wanted to improve the coding process. The coding process means this assigning of attributes. So telling how wide is the cycling infrastructure, if there are cars passing by or not, what type of barrier or light segregation we have on the side of the infrastructure. So let's start with the first one. And what we did in the first point is that we Manuel already mentioned, the main project from USPA, the space program from the European Union, it's to test their solutions. And Galileo is a geo positioning system, just like GPS. Actually, the right name, they call it is GNSS, Global Navigation Satellite Systems, I believe. So Galileo is one of them. And it's a constellation that is very powerful in Europe and in urban areas. It's been super helpful. So let's see what we did. As I said, we developed a mobile app. We collect images. First, we were actually doing this without knowing much about the different positioning accuracy. So we found that some of the photos, mainly in urban areas, when we collected them, when we expected a straight line in here, we found that sometimes we are cycling on a bicycle, so we didn't really get the best positioning system. What we make sure is that now with the mobile app, and actually every phone now from the last 2-3 years is using multi-constellation, so basically using GPS from the US, but also Galileo. So we can improve the positioning. While we're cycling, we're just automatically collecting images, just like Google Street View, but we don't need antennas, we don't need super high technology hardware, we can just mobile phones. Business-wise, it's super interesting. So we can collect super accurate photos and positioning just with a mobile phone, thanks to Galileo. So we tested this as part of the project. And then the second thing, it was also very interesting. So we did two things. One is that we're working on a computer vision model to analyze the images that we collect. So we want to make sure that we make the process automatic as much as possible. And also analyzing other sources of data. What does that mean? And I will tell you more about Copernicus and their digital elevation model. So do you remember these 40 attributes from CycleRAP? We have objects on the road, we have the surface, we have the width of the cycle lane, if there's a barrier, if there's cars passing by. So there are many things that we want to analyze. So this is what we're doing, and that's what we were doing and still doing at some point. We're doing some manual coding. So imagine we are doing for each 10-meter section all this coding. So basically clicking and saying, oh, what is this? Okay, I see that this photo is a two-way. Yeah, we do have segregation from vehicles. Okay, perfect. Can we consider that as delineation? Yeah, it is. There's this sort of zebra in the middle separating the two ways. Okay, all that for every 10 meters. So this is it's time consuming. Direct time consumption. I say direct because you are clicking and it's clicking again and clicking again. But I say indirect because you need to assign one person to do it. This person is a technical person that needs to learn. It's not like anyone can do it. We need to follow the CycleRAP standard. So there's some knowledge to be put in there. We need to do some project management to assign the person. So also indirect time consumption. Obviously, this is costly in terms of money. And the last thing is that is prone to error. If you're doing this and then you check the next image and then the next image and then you go on and go on and on, this could make it a little bit tight, and it's completely understandable. There's a lot of information, a lot of data to be understood. So imagine this example in Barcelona with this project. Imagine that there's this selected routes, 80 kilometers. That's approximately 88,000 sections. Each section with 40 attributes. That's over 3 million data points, as I call them. Imagine doing click on each of them. So it's awful. It's difficult. So what we're trying to do is to help now the manual coders and also to make it automatic, also to find a point in which we can rely on different sources. So we're developing a computer vision model that with the image, we can analyze the width, if there are potholes and cracks on the ground, what type of surface, and all these attributes. We actually are quite advanced in analyzing some of the attributes, not the 40 of them, but some of them. So it's already adding a lot of, we're advancing on this. And I have this asterisk here just to say that, okay, our model is in beta version. I'm saying this because this is relevant. Computer vision models are not built in a weekend. So So what we did in the model is that we are improving the precision, the accuracy. So far, we sort of rely on it, but we still need human review. That's why we have the review process, not only to review the manual coding, but also to review the computer vision model. Well, yeah, but we believe that in the really near future, we can have at least a few attributes, 1/3 of the attributes analyzed automatically. One more example. I love this slide because it looks a little bit like from the future. It is, but it's actually a fact sheet from ESA. So ESA is the spatial agency, so very linked to USPAT. And basically, what this fact sheet is talking about is about the digital elevation model that we are using as an external source for our analysis. And this is the only thing I'm going to read from my presentation because it's going to be quite clear. So this model, the Copernicus DEM, Digital Elevation Model, is a digital surface model that represents the heights of natural and human-made features on Earth's surface, including terrain, vegetation, building, and infrastructure. So it's not the height above sea level. It's analyzing if there's a breach, we can see the elevation at that specific point. And you can see here at the bottom, we see the coverage and resolution. Worldwide, we can have down to 30 meters. So basically, we see the world as a screen and we have pixels. Every 30 meters, we will have one dot saying, okay, this is the elevation in here. But in Europe, we can have that down to 10 meters. Extremely precise, extremely precise. And this is very relevant because one of the attributes that we use for CycleRAP is the grade. So there's a slope. What is the slope? So when you can analyze if it's less than 5% or more than 5%, for example. So basically with this, it doesn't matter if you're on a bridge, you're cycling on a bridge, you will know the slope, if there's a grade in there, because we automatically will have this data from the elevation model. Of course, we convert the elevation into the slope, into the grade. When you have 2 points, we need to analyze it. But it's simple. What does that bring to us? 80,000 data points that are automatically coded for that project that I mentioned earlier. That's 80,000 clicks that are saved. So if this is just one project and we can do another project, and this is one source of data. So we're testing as part of Julia that this can be done. And this is business-wise, this is what we're analyzing. Obviously, this is reducing the error, reducing the time, reducing the cost. So it is quite relevant for us that Copernicus is available. Okay, last little bit. Where is Lane Patrol now? Where are we now? So we've been working in different contexts, in 3 different continents. Thanks to iRAP, thanks Monica. Our project, the first project we had in Barcelona and Madrid, was mentioned in the New York Times, which was very interesting, also for marketing, you know. But what we see is that users in different areas of the world they already trust iRAP. When we explain the CycleRAP methodology, they trust us to say, okay, this is there's data to help us decide what we're going to do. So this is very interesting. And I'm going to just show you some of the examples that we've been working. So in Skopje, in North Macedonia, we analyze the whole network. We analyze main roads versus other roads, secondary roads. In Oxford, from selected routes, where we analyze mainly some analysis of off-road and on-road infrastructure, and we compare it. And then we use the forecasting scenarios tool to create the scenarios based on the data that we achieved. So something similar that as I mentioned in Valencia. In Abu Dhabi, what we did is we created scenarios where there's no cycling infrastructure at all. We analyzed it, and then we create different scenarios to say, okay, what you can do here, what will be the most effective in terms of risk to building here. And that's where we are now. So if you are more interested in knowing how CycleRAP, Lane Patrol works, if you want to just push in your city, whether you're a representative or you're a practitioner, just we can talk. This is my email and my LinkedIn profile. And I think we're going to go to some questions now, I believe.
Thank you, Manuel and Jose. Please don't forget to put your questions in the chat.
Okay. So hello everyone, my name is Andrea Lopes Azevedo. I work at Polis and also at the PHOEBE project. So while you think about your questions, I know that we have little time, but maybe Monica, I go to you for a question. How important do you think that AI is for the future of the PHOEBE framework and other tools like CycleRAP?
Thanks, Andrea. I think AI, what it is an enabler. I think what Jose was just showing about automatic detection of road attributes for these sorts of models is really important. And it's important because you really need to understand the road environment in order to understand what to fix with it. It's one thing to be looking at things like conflict data, which is a good and a good source of information as to where there might be issues, but unless it's triangulated with what the road environment actually says, it's very hard then for a road authority to make that jump as to, well, we can see we've got a problem here, but we don't really understand what the problem is. Is the harsh braking because kids are crossing a street in a place where they're not expected to cross a street, or is there harsh braking because, I don't know, there's a post box on the side of the road and everyone remembers they've got to put a letter in. I mean, and I'm not using those examples lightly. They are very real scenarios that you face when you're looking at different kinds of data. What AI can help us do is really accelerate the gathering of that information. iRAP's been working with its star rating models across many countries. I think we're up to now 130 countries worldwide over 20 years, and they started as very much a manual process. And so where we are looking to go to in the future is making these processes far more automatic and easy for the gathering of that information, but it's also about the analysis of that information and being able to understand the layering of different data sets as well in a geospatial way. So the analysis is another aspect where AI, I think, can really bring a lot, and that's what we're working towards with the PHOEBE project. It is really about getting some very powerful simulation tools and making sure that the risk and safety models are built into those, but then also that we can understand what the human behavior elements is. So we're using data sources like telematics, which do have the harsh braking and swerving sorts of information coming in. And it's about bringing those things together. And I think AI will just make this easier and more approachable as we're going forward, particularly for these more sophisticated and multi-dimensional approaches to evaluating risk.
Thanks, Monica. So a lot to look for. If anyone has any questions, please just say so. Otherwise, maybe Manuel, just the last one before we wrap it up. How can the space technologies like Galileo and Copernicus enhance cycling experiences, especially in navigation safety? Do you have anything to share before we leave?
Yeah, definitely. Thank you for the question. Yeah, so Galileo definitely can help providing a better positioning, and this HAS system that can provide centimeter level positioning can really help on different applications, not only in online patrol, but for instance, turn-by-turn navigation on urban roads that have a lot of noise and it's difficult to get high aggressive signals. But also for safer cycling by detecting like exact locations in case of accidents. For instance, Copernicus can help with the air quality and provide real data on weather conditions and terrain as well. That can help also as well bikers even in like safer trails and even outside of the urban environment.
Great, thank you very much. So I think we should wrap it up, right? It's already our time, but I want to thank everyone, our speakers, and also everyone who joined us. If you have anything that you think about after, there was a lot to absorb. Thank you very much. Just feel free to reach us. And thank you, Monica, Jose, and Manuel.
Thanks, everyone.
Thank you very
Appreciate you joining
much.
us today.
Thank you.